Hello, today's video is going to be about some of the mathematics behind radioactivity and half-life. I'll try to keep it as brief as I can. I'm not going to go over a lot of the theory that sticks with this topic. Instead, I'll just email you a video made by Professor Dave and probably Crash Course Physics. They do a really good job of dissecting a bit more of the theory aside from these documents you can read found on June 3rd or June 4th that you should probably read, and it'll give you a good idea of what exactly I'm talking about. But as far as just sort of walking you through a lot of the mathematics, that's kind of what this video is going to be about. So, but I will just touch on a little bit of the theory just to kind of remind you, even though I know you know already, but I'll say it again anyways. So this is a rough description of our atom. We know quantum mechanics says it's more of an electron cloud rather than these orbitals, but for all intents and purposes, this is close enough for our purposes. Inside the nucleus of an atom are known as nucleons. So that's where the protons and neutrons exist. Outside of the nucleus are the electrons. And that's basically all you really need to know at this point. So the mass of the proton is approximately this in kilograms, or this in standard atomic unit format. Typically, when we do a lot of our energy calculations, we're going to need to use it our value in kilograms, but when it comes to some basic chemistry or physics, or just figuring out some of the masses involved, you can usually start off with just the atomic mass notation. The masses that are found on the periodic table for all the elements are typically in a simplified form of atomic mass units. So for instance, oxygen would be just 16 atomic mass units, carbon is 12 atomic mass units. Often there's some decimals involved, but if you're in chemistry, especially at the high school level, usually you just need to know what it is to the nearest 2 decimal places, if that. Most of the time, just you don't even need decimals. Now, when it comes to nuclear physics, nuclear chemistry, I strongly recommend that you keep all 6 of these decimal places whenever you are about to do a lot of the mathematics involving energy calculations or even mass differences, because more often than not, even though you'll start with maybe 9 digits or 8 digits or 7 digits, whatever you start off with, it will get quickly simplified down to either 2, 3, 4, or 5 digits, depending on the context of the question. So it's going to be a painful process, but do keep all of these decimal places. There's a reason why they're on here. So mass of a proton, roughly this is what should be seen on your equation sheet from the start of the year. Mass of the neutron, so just slightly heavier than the mass of a proton. And then of course the mass of an electron by and large is pretty minuscule in comparison to these two. So less than 1/2000th of the mass as essentially. So those are the number we're going to work with. As far as standard atomic notation, again, this comes back to chemistry, back in good old grade 10. When you write out your elements, you write out their symbol, such as you see it. If it's 2 digits, the first one is the capitalized one, the second one is lowercase. So that would be chlorine, of course. Chlorine has 17 protons and its atomic mass is 35 atomic mass units. Now, when it's written in this form, typically we don't involve all those decimals that you saw on the previous page, right? This is just the simplest form of writing it down. So if you're actually writing it down in standard atomic notation, there shouldn't be any decimal places. That's just there as a rough approximation. To find your number of neutrons, you would just take your atomic mass and subtract your atomic number, because the atomic number is the number of protons, and that should give you your number of neutrons. So for fluorine, you would just basically, as it's written, 35 minus 17 gives you 18. That's your number of neutrons. So the mass numbers that are on your periodic table, those are the average masses based on all the other different isotopes. So isotopes are elements that have the same number of protons but different number of neutrons. So it's the number of protons that provide the physical properties, chemical properties of the actual atom, and the number of neutrons can differ. But for a lot of the elements, especially the smaller ones, the ones in the periodic table are usually a reflection of the most abundant isotopes. So for instance, carbon-12, about almost 99% of all carbon found on Earth, and we're pretty sure in the universe, is going to be carbon-12. You have trace amounts of carbon-14 in your body, and we use carbon-14 for carbon dating. So carbon-14 has 2 more neutrons than normal carbon-12. Carbon-13, about almost 1% of the carbon that's out there in the universe is carbon-13, but just small trace amounts are carbon-14 and carbon-11. So those are just examples of isotopes. The same element, they have the same chemical properties. They just have, in some cases, fewer or more neutrons than the normal. So those are isotopes. So unstable isotopes can build into some kind of spontaneous disintegration of the nucleus. So that was first proposed by Marie Curie after they're trying to figure out what was going on with uranium, which was discovered by Henri Becquerel. Like, okay, well, something's happening here. It's emitting something from the atom. It's causing photographic film to develop. Marie Curie is the first one to kind of say, hey, maybe something's going on with the atom inside the nucleus of the atom. At that point was quite radical because, you know, you can't break it down any more than that. So that was unknown to them. So if you end up getting an unstable isotope, it depending on the size of the actual atom. So in this case, radium here, this little GIF that keeps on repeating itself. Radium is a large nucleus. So the larger nuclei, anything greater than bismuth, is going to often emit an alpha particle. I'll get into that in a second. In this case, the alpha particle gets spat out, and the nucleus itself decreases its mass by 4 units, so 4 nucleons, so 2 neutrons and 2 protons. And because 2 protons got emitted, so this is the alpha particle, our our atom actually changed. It changed from radium to radon. So this is known as transmutation, right? Or if you go back a few hundred years, they called this alchemy, and then they tried you for witchcraft. But apparently this is a real thing. So this is exactly what radioactivity is, okay? The 3 different types of radiation were kind of figured out by Lord Ernest Rutherford over in Montreal. So he basically just took a container of radioactive source. I believe it was cesium. I actually can't remember this exact moment because my brain is dead. So he fired it at some kind of photographic film, and of course he lined it with lead because it was determined at this point that radioactive particles had a hard time going through lead, and so they had this lead shielding on there, and they passed it through, and of course it developed on photographic paper or fluorescent film, if you will. And then when he found that he put a magnetic field in its presence, it would cause the beta particles. So it would cause some particles to go to the left, some particles to go to the right, and some particles went straight through, which kind of gave us a foundation of the difference between the 3 particles that come from inside the nucleus of the atom. Alpha particles, if your magnetic field is coming out of the page, curves to the right, and so therefore it must be positive if you apply the right-hand rule. Gamma particles just go straight through without curving in the magnetic field, so that tells us there's absolutely 0 charge gamma particles. And beta particles veer to the left with your magnetic field going out of the page. So again, if you use your right-hand rule, that tells us that the force is going in the exact opposite direction as what the right-hand rule would suggest. So therefore, beta particles must be negatively charged. And if you look at the difference between how far they were deflected, alpha particles gives you a good indication that it's a heavy mass, and beta particles is a much, much lighter mass. So alpha particles is heavier because it turns out it has a mass of 4 atomic mass units. So it's basically a helium ion, whereas beta particles are chemically identical to an electron. So much, 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 much smaller than the alpha particle. So nuclear transmutation, there's pretty much your official definition, the conversion of one chemical element or an isotope to another. So basically the whole notion of your chemistry, your elements cannot change. Well, that's kind of a lie. Elements can change based on nuclear decay. We definitely don't talk about that too much in the younger grades because we're having a hard enough time trying to get the chemical equations down so that students know not to actually change, say, carbon into oxygen randomly. But it can technically happen. That's when you start doing nuclear chemistry, but that's not done at the Saskatchewan high school level. So, there we go. This is an example of alpha decay. So again, alpha decay occurs when you have really large nuclei. If you have an unstable nuclei, typically most nuclei above bismuth, so element number 83, if it has an unstable isotope, it'll probably undergo alpha decay. So basically, in this case, the plutonium has an atomic number of 94, it's quite unstable. So this is plutonium-240. When it undergoes alpha decay, it spits out an alpha particle. So if you notice here, it spits out 2 protons, and so the proton number goes from 94 to 92. Once you know that you have atomic number 92, you know what your actual element is. So 92 protons means you have uranium now, and it's just a matter of going, okay, well, I started with 240. I'll use this diagram over here. This is the decay series. If you start with 240 atomic mass units, spit out an alpha particle, that's 4. Well, 240 minus 4 gives you 236, and that's typically how you'd show an alpha decay. The element that you start with, this is called the parent nucleus. The particles you end up with are known as the daughter nuclei. So in this case, plutonium-240 undergoes alpha decay and becomes uranium-236. Uranium-236 is also unstable, so it would probably undergo some more further decay. But we're just talking about a single particle of plutonium and a single particle of uranium-236. So this decay series wouldn't stop here. It would keep on going, but as far as just trying to isolate a single alpha decay, this is what it would look like. So beta decay is the other type. There's a couple of different types of beta decay. The main common one is when you have a neutron, it will spontaneously decay into both a proton and an electron. Inside the nucleus, the electron gets kicked out, right? And because that electron came from inside the nucleus, it is known as a beta particle, right? This is, it's not held inside due to the weak nuclear force, and so because of that, it's not strong enough to keep it inside, and therefore, it just gets spat out, all right? It comes out at high velocities. Also, it spits out an antineutrino along with it. That's something you don't typically have to worry about for our context. It's just, at this moment, it's just another particle that comes with beta decay. Antineutrino has basically no mass. It has no charge. That's contested a little bit, but as far as you're concerned, you can go with those properties and say, hey, that's close enough. So beta particle, again, is basically an electron. The other type of beta decay is known as positron decay. So it's also beta decay, except it's the opposite effect. A proton decays into into a neutron, and instead of spitting out an electron, it just spits out a positron, which is the antimatter version of the electron. So those are the 2 types of beta decay. This beta decay is the most common one, where the neutron decays into a proton, but the other one happens as well. So if we were to write an example of this one, so let's just take neptunium-293. Let's just suppose it undergoes beta decay. What we do next is we kind of just do a quick little bit of math. So the little bit of math that we do is, okay, so if it's going to undergo beta decay, we'd write down the symbol. So beta particle typically looks like this, is the Greek letter beta, so it's just B with a little tail. If you'd much rather write it down as an electron, that's fine, but you don't have to do both, right? Just one or the other, that's good enough. And then from there, you just do a little bit of math. So if you had 239 atomic mass units and the beta particle, which is basically an electron, so again, it's 1/2000th the size. So as far as no decimal places are concerned, that's basically 0. So that's why 0's up there. So your daughter nucleus should have 239 atomic mass units as well. So when neptunium undergoes beta decay, you essentially just go, okay, well, you had 93 atomic mass units. So the neutron decayed into a proton, so we ended up with 1 more proton. Or you can just kind of reverse the math. What plus a -1 gives you 93, and so of course you just do the basic math and say 94, great. And so then you look up on your periodic table what has 94 protons, and that of course is plutonium. Okay, and that's basically all you do for that. When it comes to beta positive decay, you would just go the opposite direction, and that would be the only thing that would change, is you'd have a positive there, and then you just have to make adjustments as necessary. So when it comes to gamma radiation, there is really no need to do a decay series for gamma radiation. There's no overall change to the actual nucleus of the atom, aside from the fact that you start with a nucleus that has high energy, so it has a little too much energy, so it's considered to be unstable. And then all it really does, it spits out a little bit of electromagnetic radiation, which is all a gamma ray is, gamma particle. A little bit of electromagnetic radiation, and then it doesn't actually change the nucleus chemically whatsoever. It's just now it has lower energy, because this is basically pure energy as it gets spat out. So gamma radiation is just a bunch of high energy photons. Gamma rays can go through paper, it can go through tin, aluminum, steel. It can go through. It's mostly stopped by lead, but thickness comes into play here. If it's ridiculously thick lead, it'll probably stop almost all of it, but not all of it. Then it gets into, I think it's the conversion is every 6 inches of, or sorry, every ½ inch of lead is about the equivalent of a foot of concrete. So you can also use concrete to stop gamma particles as well. So very highly penetrating. X-rays aren't part of nuclear radiation because X-rays don't come from the nucleus of the atom. X-rays come from a rearrangement of the electrons. So that's not technically part of nuclear radiation, although it should be at least mentioned casually. Neutron radiation does come from the nucleus of the atom. So these are heavy particles that don't have any charge, but they have a lot of mass because, of course, they're both equivalent of a proton. So we typically have to make something undergo neutron radiation. So I know from my experience in the oil field, if you want to create a neutron emitter, you would take americium-241, which is typically an alpha decay emitter, alpha particle emitter. And if you dope it with beryllium particles, the alpha particles would collide with the beryllium particles that are mixed in with the americium, and then the alpha particles would basically disintegrate and you'd have stray neutrons getting spit out. And these stray neutrons are pretty dangerous because when they interact with your human body, the human's full of lots of water and water has a lot of hydrogen. So these neutrons would actually excite the hydrogen that was inside your body, which is not overly great as far as your safety is concerned. So typically if you have neutron emitters, they emit gamma radiation as well. So usually if you have something that emits neutrons, it's spitting out other particles as well. So they're typically highly dangerous. It's also typically one of the ones that are often ignored if we're just talking about very basic radioactive decay. So these things do decay. So the three examples that I talked to you about, the main ones, alpha, beta, and gamma. Alpha decay and beta decay are going to change what the actual element is. So that's the whole transmutation, which means we have to really talk about half-life. So every element has a half-life, which basically talks about the predictability of how long it'll take for half of the mass or half of the sample that you have, all the individual elements that make up the whole sample, how long will it take for half of it to turn into something else. So we're not talking about what its final stable state is. Just suppose you have a kilogram of mass, right? So if you involve Avogadro's number into this kilogram of mass, you know that means you have a ton of individual particles. So it's impossible to predict when any individual element is going to spontaneously disintegrate. It's just not possible for us to predict any one, but you can predict fairly accurately a large collection of them. So that's where half-life kicks in. And so basically, if you had a kilogram of mass, one half-life later, you'd probably still in total have about a kilogram of mass, except it wouldn't just be all one thing. So if you start off with a kilogram of uranium and it was radioactive uranium, a few billion years later, I'll get to the number in a second. I usually get that number wrong when I rely on my memory. A few billion years later, half of it is still uranium. The other half is a combination of thorium, radium, lead, all sorts of other things as it's undergoing all of its individual decay series, right? So in this case, if I use this as my example, it's obviously not set up so the top half versus the bottom half, but this is the picture I'm going with. So this would still be the uranium, and up here would be all the other individual new things that it decayed into, all right? Another so many billion years later, half of whatever remained has now decayed into all the other tiny little bits, right? Another few billion years later, another half-life goes by and it goes on and so forth. And it is a decay series where it actually exponentially goes down and down and down and down, right? So 2 half-lives later, you have your 1/4. 3 half-lives later, you're 1/8 of what you have, right? Up to 5 half-lives later, you're 1/32 of whatever you originally had, and it can go on and so forth, right? So that's basically the relationship of a half-life, right? Where the time is just random times, depends on the element. There it is. So if it's uranium-238, I was going to say that number, but we'll never know now. I typically remember that as about 4.5 billion years of a half-life. Uranium-238 is natural in the ground. Uranium-235, about 0.7% of all naturally found uranium is uranium-235. This is the uranium of choice when it comes to nuclear reactors and nuclear weapons, unfortunately. And its half-life is quite a bit shorter than uranium-238. Carbon-14, you have that in your bodies. Its half-life is about 6,000 years. And so that's often why I hear anything from, oh, carbon dating is only good for anywhere between 20 and 50,000 years. After that, there's just not enough carbon in available, carbon-14, to actually detect how old something is. Silver-94, as you can see, it doesn't last very long. And if you look at your periodic table, in the very, very bottom line, the one that's disconnected, you have all these new ones. Depending on which periodic table you look at, a bunch of them are called something or other. They all have new names. I just don't remember what they are because they're still brand new. They all have half-lives of like up to anywhere from microseconds to nanoseconds because they basically have to be man-made. So their half-lives are ridiculously short, and in some cases, I think only 6 or so particles have been found. I think that's element 118. I just don't remember the new official name for it. So gives you a rough idea. This is what a transmutation decay series looks like. So uranium-238 is the most popular one to show how it actually changes into 13 individual things, starting at uranium-238, undergoes an alpha decay and then 2 beta decays, as you can see down below. Its first alpha decay makes it thorium, and then it undergoes 2 beta decays back to uranium. But the only difference between this state versus that state is we have 4 fewer atomic mass units, right? So that's the difference between these two, but it's chemically back to the same as uranium-238. And you can see it undergoes quite a few more alpha decay series. So when we're talking about the half-life of roughly 4.5 billion years, we're just talking about this one right here. Right? So obviously over the 4.5 billion years, some of this process is going to happen. Some of it's going to go all the way to lead. This is the most stable state, lead 206, but anywhere for whatever masses are still around on that chunk of 1 kilogram, you could be at any one of these individual points in time because, again, this is all spontaneous decay. So this would be one of the many equations that you would see for the half-life. There's different equations, right? The last equation I remember playing with in university looked more like this one, but I don't believe all of you guys have started working with that letter E, so let's just assume that we're just not going to touch on them because they also involve different tables of values. I've also seen it written down either as A, which is referring to the mass or even just the activity of it. But I've seen it represented instead of A as N as well. So depends on what textbook you're looking at, really. I'll just hide those. The textbook that you have access to, or at the very least the PDF files I put on my main class calendar, has this as the equation, so that's the one we're going to use. So A is the remaining mass of the element, A naught is the original mass of the element, T is basically the measured time. So suppose it's 3 years later, how much, I don't know, uranium do you have after 3 years? And H is the known half-life. So very often in a lot of physics, you're told to convert all your time into seconds. Typically, if you're given a half-life of, say, 30 years and you're just given some random time, just make the 2 time units the same. I don't care if it's years, days, hours, avoid months. Seconds, it doesn't really matter as long as they're the same, because the purpose here is that the units should cancel. Likewise, you were told typically to use masses in kilograms. When it comes to this half-life equation, if you're given something in grams or milligrams or micrograms, don't bother converting it to kilograms, because whatever you were given, just assume that you're going to keep those same units as you move forward, right? So the mass unit probably shouldn't change, just as a heads up. Keep it simple. So if you ever need to solve for the exponent, I'll assume you've seen logarithms at some point. If you use logarithms or natural logarithms, this ratio should be identical, because natural logarithms are based on logs. I think by now you should have seen this in your math classes. So that's just a quick little conversion to actually solve for whatever that exponent is. All right, so log of the ratio of your leftover mass divided by your original mass, all divided by the log ratio of 1/2, so log 0.5. This will probably give you a negative number, this will probably give you a negative number, and those two negatives will cancel out in the end. And that'll just give you the ratio of your measured time divided by your half-life time. And if you know what your sample is, you typically know what the half-life is. I've also seen questions where it asks, what's the percentage remaining when you're doing some of your math problems? So the percentage remaining is just either looking at, depends what's given to you. If you're given the mass that's remaining and you know what mass you had originally, well, that's just a ratio of the two, then multiply by 100%. If you just know what your half-life is, so that'd be H, and how long you've been monitoring this for, you don't have to know what you started with or what you ended with. You can just look at just the half-life portion of it, right? This math portion of it, figure that out and just multiply by 100%. And I'll just give you a percentage of what should be remaining, regardless of not knowing how much you started with. So that's all that equation is getting at. So I'll just do one quick one. And I think that should be good enough for most of you guys. And you can email me if you have other problems. Neon 19 has a half-life of 17.22 seconds. Right before I made this video, I quickly looked it up, and there's, you know, just over a dozen, I think fewer than 20 individual isotopes of neon. So neon 19 is just one of them, and as you can see, its half-life isn't very long. So what mass of neon 19 would remain from a 100 milligram initial sample after 30 seconds? So 30 seconds is longer than the actual half-life, so it's going to go through about at least one half-life. So I know it should be less than 50 milligrams. But to get the specifics, you would just kind of make sure you recognize which one is which. So if you know the half-life is 17.22, then H should be 17.22. We're looking for how much remains after 30 seconds, so that's what T is going to be, and we start with 100 milligrams. So using that equation, you plug in all your terms, right? So very often, some students make mistakes here as they enter this stuff in, because and depending on what their calculator is, they just try to enter all the numbers in as they read from left to right. I don't know what your calculators would be like. Some of you have the ability to make an exponent and do this off to the side, right, inside the exponent, and that's great. Some of your calculators won't, so you might have to solve this independently somewhere else and then put that number into the exponent for your 1/2. So you'll have to figure out what your calculator does. So you can just try it. Pause this video, try it, and see if you get the same answer I get. And if not, if you can't figure it out, just send me an email, and we might do a Zoom or a Google Meet, and I can usually figure out each of your individual calculators. So if you do it separately, right, my calculator, I can do this all in one step. But at the very least, figure out what that ratio is and make that your exponent if you can't do it all in one step. And then essentially just work it through. All right, so you have about 30 milligrams left over, all right, after it goes through 1 and a bit half-lives. So on the main, I forget the date, there it is, on June 4th, if you go to this PDF right here, there should be some questions. Do questions 1 to 2 on page 332, do questions 1 to 3 on page 333. They won't take you very long. And I believe I put answers just on June 4th, because I don't believe it's not in your textbook. Not textbook, it's not in your print-off package that you got from the website. So give that a read, try those questions, and then email me if you have questions of your own.